Greetings and welcome to the PLSQL channel, a series of video trainings on the Oracle PLSQL language. My name is Stephen Feuerstein, and I'm a PLSQL developer just like you. This lesson is part of my series on writing maintainable code, and the focus of this lesson is leveraging readability features of the PLSQL language. Some quick reminders. Visit my PLSQL Obsession website at toadworld.com/sf to download the code that I'll be running in this lesson and all my other lessons, as well as supporting PowerPoint documents. So just at PLSQL Obsession, you can click on the demo.zip link to download all of the files that I use in my demonstrations and trainings and even development. Click on Training Seminars and Presentations to drill down to a page containing PowerPoints and PDFs of my trainings, both for these video series and for my full 2-day and 1-day trainings. Second, make sure you're comfortable with the material covered in the previous lessons in this series. The first one was discussing the importance of maintainability in development and also, as a part of that, regression testing. And then I covered the role of standards in creating maintainable applications. Now I'd like to talk about writing readable, maintainable code and specifically leveraging features of PLSQL that will help you do that. And actually, it's pretty easy in the world of PLSQL to write very readable, self-documenting, easily maintained code. And this should be a very critical primary objective for any and every developer. In other words, we need to write code so that it tells its own story. Rather than writing comments explaining what we've written, it should just tell you by reading the code what is going on. Here's what we'll look at in this lesson: end labels, subtypes, name notation, one way in, one way out. But first, let's just get an appreciation of PLSQL's natural readability, at least assuming that you can read the English language, which would be very helpful when taking these lessons as well. So let's compare Java and PLSQL. What you see at the top is a Java class, a very simple Java class, that has a single method inside of it. And here we have a PLSQL program which creates a procedure. Now, interestingly enough, these pretty much do the same thing. This is what stands for a procedure inside Java. And the reason I know it's a procedure is that it's a static void method. And when you see void, that means that the program, the method, doesn't have a type. It doesn't return a type. Therefore, it must be a procedure. Also, there's no return statement inside of it. So I can look at this code and I can deduce that it's a procedure. But I look at PLSQL and it says it's a procedure. Where does the executable section begin in a Java class? Well, actually, there isn't really a separate executable section from, say, the declaration section. But the body of the code for this method starts with an open squiggle and ends with an end squiggle. In PLSQL, where does the executable section begin? With the word begin. Where does it end? With the word end. Nice and easy and straightforward to look at, read, and understand. Now, I'm not saying that it's hard to read Java. Certainly after a very small amount of time with the language, if you haven't already done this, you'll be able to read this kind of code and it won't baffle you completely. You won't be put off by the open squiggle and closed squiggles all over the place and the need to infer or deduce things about your code by saying, oh, since it's void, it must be a procedure. It's not that hard to pick up programming languages. My point is simply that even though Java is much more powerful and you can do a lot more with it, PLSQL is much easier to write and to understand. And I think that's just something we should appreciate about the PLSQL language. There's usually trade-offs in a language, and part of the trade-off here is less complexity in PLSQL, more readability, or at least potentially more readability, unless you make it really, really hard to read that code, which of course we don't want to do. So, let's take a look at some key readability features. First, end labels. We can specify the name of something not only when we start it, but when we end it. Program units, loops, nested blocks. Subtypes. We can create application-specific data types that greatly improve the readability of our code. Name notation. When we call a program, we can explicitly associate the formal parameter with the actual argument. And then we'll talk about some classic structured programming advice. One way in, one way out. And labels. Any PL/SQL structure that has an end statement, end block, end loop, end case can also have a label appended to that statement, a name. End labels make it easy for you to see at a glance the place in your code, what you're ending. And that's especially important with large programs with lots of subprograms, large packages with lots of subprograms. And you sometimes have elements in your PL/SQL code that are unnamed. For example, nested blocks, loops. You can actually give those sections of code names by using PL/SQL labels. And then you can use that name both within the scope of that code and also to specify the end of it. Let's take a look. So in my endLabel script, I create a package called endLabels, and I can put the name at the end. Now, of course, I could just do that. And in this tiny little package, it's no big deal. I know which package it is. But in a larger body of code, it would be harder to understand. In fact, let's just open a larger body of code. I'm going to go to the code that I use to generate the test code in Quest Code Tester for Oracle. It's an automated testing tool. This is a really big package, and it should be showing me yep, there we go. You can see it's got lots of programs in it. And way down at the end, I have the name of my package. Now, I don't have to include the name here. I could leave it out. And it's not like it's a big deal here. I know I'm in the queue generate package, but it's a nice little reminder of what I'm working on. Let's go back to the endLabel script. But you can not only provide endLabels for your program units at the schema level, also within a given program unit like a package body, when I create procedures, I can also specify at the end of that procedure the name. And if I have local or nested modules inside my procedure, I can and should provide the names. And here's a situation where, again, it's very small incremental changes to your code that can greatly improve readability. This could look just like this. And your code will still compile. And it's not that it's terribly hard to read. But when you're working with a lot of code, being able to be working on this program, let's go down, say, to here. Oh, now here are some examples of inconsistency. I've got some endLabels, some don't. That's a bad thing for readability all by itself. You should be very consistent. But when I'm starting to work on a new program and I'm here, I can immediately see the name of the program above me. Without this, I wouldn't know what it is. And that small amount of additional readability can make a big difference when you're working on complex code. So the general rule would be to always add a label, an end label, to your subprogram units. Now, if you're anonymous elements, for example, my anonymous block, my nested block, I can give a name to that block using a label. A label are two less than symbols, the identifier, and two greater than symbols. And if I give a name to my block, I can end the block with the name. And also I can reference local variables. I can qualify references to local variables with their name. Now, I might want to do this if I have an actual variable with the same name outside here. For example, my outer block contains a local variable, which is a date. And I want to make sure that I specify which one I'm referencing here. That's a nice way to use this label. Of course, better yet is to never do this. Don't declare the same variable in multiple scopes, multiple levels. But the bottom line is I can give a name to my nested blocks, especially if I have a big nested block. It's very important to end it with a name so I can see what I'm working on when I get to the end. Better yet is to not have nested blocks and instead use local submodules, which is covered in the last lesson in my series on maintainability, modular construction. In addition, I can give names to loops. So there's my loop, give it a name with a label, and I can say end loop with my loop. So if you are the sort of person who writes really big loop bodies that go on for a page or two, and you want to remember what loop you're ending, or make sure that anybody coming along later, when they see the end loop statement, can know what loop you're ending, use the label, give it a name, and explicitly tell everybody what you're ending. Subtypes. Now, I'm sure you're all familiar with %type and %row type. And you use that feature to anchor back to an existing data type, either a column in a table, or a variable in another package, or a record in a table, and so on, when you're declaring a new variable. But sometimes you can't anchor back to a database element. Sometimes your data is derived from multiple pieces of data from the back end, or it has no representation in the back end. In that case, you can always use a subtype to define an application-specific data type, a single point of definition for that type of data, and then use it in all subsequent declarations. And the really wonderful thing about this is that you can declare your own types and give them application-specific names, and hide the details, hide the implementation behind those names, making your code more readable and much more maintainable. This is especially critical when working with complex structures like collections of records, nested collections, and so on. This topic is covered in much more detail in my series on Say Goodbye to Hard Coding, but I'm going to show you the basic idea behind subtypes and their value, and then I encourage you to check out that separate video series for the full details. So first of all, let's take a look at why or where I might want to use a subtype. Here's an example of a hard-coded data type. And this data type, LName, is going to grab the value or get the value from last comma first, so the full name of a person. Now, I could do a percent type against last name. I could do a percent type against first name in the employees table, but I can't do a percent type against both. So instead what I tend to do is something like this. Look at the structure of the table. First name is 20, last name is 25, that's 45, plus 1 for the comma, that's 46. I'm going to double it. Make it 100. That's way more than big enough. It'll never get to be that big. So I make an assumption about what's going to happen in the future with my code and my data. And I say to myself, this will be big enough. And then I grab the value in my query and I work with my data, and it seems okay. But later on, years from now, the database, the DBA, might expand the size of these columns. The total size might exceed 100, and I might start getting errors from this code. So what you should do instead, if ever hard-coding a data type like this, of derived values, or in any case, any kind of hard-coded data type, what you should do is something like this. Declare a subtype. Here's a subtype called full name. And all it's doing is hiding the definition of varchar2, 10,000, 1,000, whatever you want it to be. Compile this package, and then, in my code, rather than hard coding it and having to make a determination about what's quote-unquote big enough, I can simply say, declare this variable to be of type package, my employee's rules package, dot full name t. So now my subtype hides the details, avoids the hard coding, and as this needs to change over time, maybe it starts out at 100, and I realize I need to make it bigger. I change it in one place, and all my application code doesn't need to change at all. So there's an example of using a subtype to hide a constrained declaration to create a single point of definition. Here are some other examples from the page on your notes in this presentation. PLSQL limits package. If I want to declare a variable to be the largest size possible, I've got a big string. So I want to declare a big string. What should I declare it as? Varchar2 what? Well, I know that the maximum size is 32,767. I'll just do that. But Oracle might increase the size in the future. So instead what I do is create a separate package, PLSQL limits, with a max varchar2 type. And then, when I'm declaring my big string, I can simply declare it as PLSQL limits and let Toad pull up them for me and pick max varchar2. So hide the underlying details, avoid the hard coding, and now my code tells the story. It says this needs to be the maximum size varchar2 possible. This contains a full name. So that should give you a sense of what's involved in creating a subtype. There's actually nothing to it. It's a trivial feature of the language. But then what you want to do is make sure that you always hide your constrained declarations and let your code tell its story by declaring these application-specific types. Name notation. So, whenever you call a program, you need to pass values for the arguments, for the parameters. Now let's talk about the specific way of referring to these elements. There are formal parameters and there are actual values. The formal parameter is the definition in the parameter list, passing in a string of this name, the mode is in, The data type is varchar2. Actual values or actual arguments are the values passed to the program when you call it. So there are formals and there are actuals. And there are two ways in PLSQL to associate the actual with the formal. One is positional notation, in which the actual is associated with the formal positionally. The first value in the list goes with the first parameter. The second actual value goes with the second formal parameter, and so on. It's the most common way that people call PLSQL subprograms. Then there's name notation, in which each actual is associated with the formal explicitly by name. And there are several different advantages to using name notation, which is what I want to talk about, certainly and most importantly, from the standpoint of maintainability. Because name notation makes it much easier to understand calls to subprograms, especially subprograms that most people don't use, for rarely used programs. It also offers a lot more flexibility in how you pass arguments to parameters. Let's take a look. So I've got a procedure here called business as usual. I pass in 3, 4, 5 parameters. These are the 5 formal parameters. I have ins, in-outs, and outs. Some have default values, some do not. And let's just get rid of that implementation now so we can just see the way it's called. There are many, many different ways to call this procedure. First, let's look at the typical fashion, all positional notation. So I pass in actual values, whether they're expressions, literals, or variables. And notice there are 5 from my 5 parameters, and Oracle simply says, okay, 5 million goes to advertising budget, lobbying dollars goes to contributions in-out, merge and purge on, etc., etc. So a one-to-one correspondence, positionally aligned. And of course, Oracle does all the implicit conversions necessary. And notice also that if I have an in-out or an out, I can't provide a literal value. I have to provide a variable to contain the value coming back. So that's positional notation, and most people's code looks like positional notation. Now, suppose I wanted to leave off any of the parameters that have default values. So if I have an in parameter with a default value, then if I don't supply a value for this formal parameter, Oracle will automatically use the default value. Now, when I'm using positional notation, I can leave off any trailing in parameters, anything at the end of the list that has a default value. So here's an example of a call to business as usual, passing in 1, 2, 3, 4 values. I don't provide anything for the 5th, and it automatically uses this. But what if I want to provide the default value for merge and purge on? Notice that there's an out parameter after it, so it's not a trailing in with a default. I cannot use positional notation to pass the default for this one. I can't say, well, just pass in comma, comma. I can't pass in a null. That will pass in a null value. There's actually no way to skip over this one and use the default value for this one with positional notation. So let's take a look now at name notation. Here's an example of